Thank you. I would like first to thank the organizer for letting me the chance to speak about my study, which is the nuclear reactions. So first I will begin with an introduction, which is a generality about nuclear astrophysics. Then I will speak about the reaction, our reaction of interest, some indirect measurement, then our tool of calculation, which is our matrix, and finally I will give some new results. So nuclear astrophysics is a mix between nuclear physics, which studies the nuclear reactions, and astrophysics, which studies the massive stars. So nuclear astrophysics studies the origin and fate of the element in our universe, and the origin of the radiation and energy also in our universe. In a star, we have two main chains, the PP chains and the CNO chain. And our interest is in the CNO chain. The first reaction that happens in this chain is the 3-alpha process. Our reaction of interest comes just after the 3-alpha process. Our interest of these reactions comes after that because it is one of the case reaction in stellar astrophysics, and the CO abundant after the helium burning affects all the formation of the lighter components. It's play a very important role of the development of massive stars, and its reaction rate is a very interesting parameter in many stellar evolution models. But we have a very important problem. The first, like I said before, the first reaction that comes in the CNO cycle, it is the alpha process. It is very known. Known means that we have an uncertainty with 10%. But due to the smallness of our cross-section, we cannot do direct measurement. So it has an uncertainty which is around 25%, and it gets very worse when we try to calculate our reaction rate. So due to the difficulties in the direct measurement at the gamma of energies, I mean that the gamma energy, which is 300 keV at a temperature of T equal 2 gigakelvin, we go to some indirect methods. Here I present some of the important direct methods. There are theoretical ones and experimental ones. One of the important theoretical indirect methods is the Coulomb dissociation, alpha spectrum following the beta decay, the asymptotic normalization constant, the new one, which is the Trojan horse method, and our main study, which is the transfer reactions. The transfer reaction in our case will be the 12C7 lithium triton oxygen 16 that has been made in 2012 at the EPN of Orsay. So in this transfer reaction, we calculate first the spectroscopic factor. Here we have the experimental cross-section and the theoretical cross-section. Due to literature, we take the S prime equals to 1. The second important parameter that we need to calculate is the reduced alpha, which has a relation with the spectroscopic factor. And the third important parameter is the partial alpha, which implicates directly in the calculation of the astrophysical factors, which has two contributions, which are the SE1 and the SE2. That's why we use our calculation tool, which called the R matrix. Also, we need to determine a channel radius to calculate all these previous parameters. We chose when our function is in an asymptotic behavior because we have only the Coulomb interaction and not the nuclear interactions, because here in this part we have the both Coulomb and nuclear interactions, but from here, which is the Whittaker function, we have only the Coulomb asymptotic behavior. From calculations, we deduce that the asymptotic behavior becomes or is present when R equals or bigger than 6.5 femtometer. Also, due to its slow variation with the energy, we prefer to calculate the astrophysical factor than the cross-section, like it's shown here in these two figures with the beryllium-7. We see here that the variation of the astrophysical factor, which varies very slowly, and in the second figure, we see the variation of the cross-section, which varies rapidly with the energy. The most important parameter in our study, or the main goal of our study, is to calculate the reaction rate. This reaction rate is obtained from this numerical formula. The SE is divided into two parts, SE1, SE2. So we will have two contributions or two partial reaction rates. We just make the addition to have the total reaction rate. So to calculate this reaction rate, or to calculate first this astrophysical factor, we need a mathematical tool called the R matrix. It was developed in the 40s, and it is used to parameterization, extrapolation at low energies. The theory of the R matrix is based on two regions. Here we are talking about the theoretical R matrix, the internal region which has both nuclear and Coulomb interaction, and the external region which has only the Coulomb interaction. Here in this figure, we are showing the case of our reaction. So, after the theory, here we show in this figure the mathematical or the semi-empirical R matrix, or as known by the code of Pierre Descouvrement. It is divided by three parts, and it has two interfaces, and it's based on a visual basic code. So the first part is our main parameters, the channel radius and the different gammas. The second part here is the key square, and we need it in the feet. This key square must be the lowest value that we need to obtain in the feet. The third part is our main part, which is the final result, or the astrophysical factor. In this figure, we showed the astrophysical factor at our energy of interest, which is 300 keV. We have a new result of the calculation of the astrophysical factor. The newest thing about this result, it was made at a new channel radius, which is 7.7 femtometer. Because if you speak about other or previous results, it was just made at a channel radius which is 6.5 femtometer. This is our new result. We see always that we have a bigger uncertainty. So we also obtained a new reaction rate, which is this. By comparing our reaction rate to previous results, we have found that it is bigger by a 1.13 to NACRE compilation, which was done in 1999, greater by a factor of 141, which is adopted in 5 means the Hammer study, which was done in 2006, and the bigger by a factor of 1.43, but then the study of my supervisor, which was made at the EPN of Orsay in 2012. So we have some perspectives. We are studying now a new method called the Trojan horse method in the LNS laboratory in Italy. It is a both theoretical and an experimental method. We also have a new code which represents the next step of the R matrix calculations. We call the Amizour code. We will try to recalculate our astrophysical factor and our reaction rate using this new code. and compared it to our previous results. Also, there are two new theoretical methods. The first one, which is a Lagrange mesh method, obtained speaking about. It was just speaking about in 2019 by Pierre Descouvrement, and Coulomb dissociation method. So these are some bibliographic articles that we have used in our study. Thank you very much.
Merci, très bien.